In this course, EE555, we'll be talking about stability theory of dynamic systems. So therefore, in this very first lecture, the very first question should be, then what is stability theory of dynamic systems? Okay. Now, to be able to answer that question, we will require 14 weeks, okay? So it will take the entire course to give an answer to that question, the question of what is stability theory of dynamic systems, and that answer will only be incomplete, okay? Because the subject, stability theory of dynamic systems, is quite deep and rich, and we will be only able to touch it from the surface, okay? So the next question could be at this point, for instance, why is stability theory of dynamic systems, or in other words, why is it valuable or useful to study or to develop a theory, a stability theory for dynamic systems? Okay. To be able to answer that question, allow me to give a simple example. Okay. For instance, suppose we have a system. System, just anything that changes with respect to time. For instance, this RC circuit, C. And let this be voltage plus minus X. This is the system, and for the system we have a model, and suppose that this product RC is 1, so the model would be X dot equals minus X, okay? So usually we will not use the word model, but we use the word system interchangeably with the word model, okay? So model is the mathematical description of the actual physical system sitting in the lab, let's say. Okay, so this is our very simple system, let's say, and associated with this system, we want to know its behavior, the behavior of the solutions. In this case, the behavior of the voltage. What happens to the voltage as time goes on? Okay, so the question is, what's the behavior? Now, for that, to answer this question, the behavior of the system, what to do is, or what we can do is, in this case, we obtain the solution from the system. Okay. And in this case, we can write down the solution. This is a first order linear time invariant differential equation, the simplest differential equation, or the simplest interesting differential equation. The simplest differential equation would be x that equals 0. Okay. Now the solution to this is x of t equals the initial voltage, and then e to the minus t, okay? Supposing r times t equals 1. And then we know how this looks like if you draw it, okay? Suppose we start from a negative voltage. What's going to happen is that the voltage will display such a curve. And by looking at that curve, we can answer now the very first question, that yes, what's the behavior of our system? The behavior is that every solution converges to the origin, to 0 eventually. 0 as t goes to infinity. Okay. Now, this situation is applicable to many cases, by which I mean, given a system, what's the behavior? Now, if this system is the result of certain design, then behavior will determine, behavior of the system or behavior of the solutions of the system will determine the success or failure, for instance, of your design. If whether, for instance, the temperature rises smoothly to the reference temperature in a room, if that's your design, or whether your circuit displays nice sinusoidal oscillations, or whether it will make chaotic jamming. Okay, it determines whether your design is successful or not. So this question, therefore, is important. Given the system, what is the behavior of solutions? And the answer to that question is, given the system, obtain the solution, and then by looking at the solution, determine the behavior of the solutions. Okay. Now, this is a nice, simple answer, but there's a problem with it. It's not applicable, okay, or it's not very applicable. For instance, if this system were nonlinear, it's a high order, then we don't know how to write the solutions explicitly. Okay? In other words, in general, for nonlinear system, or for time varying system, or for both, we cannot write explicitly the solutions. Okay? So we have to skip the middle step. And without the middle step, can we still say something about the behavior of the solutions without knowing the exact explicit solution? Okay? The answer turns out to be positive. Okay, and that's a very important observation. Okay, made by the Russian scientist Lyapunov and some others. It turns out that it is not always, but sometimes still possible to determine the behavior of the solutions. Or, in short, we can say the behavior of the system without knowing the exact solution. Okay. Now, we will see how that's possible, in what ways that's possible. But for this, if we return to this simple example, here's one way. For instance, let's define the function v as 1/2 x of t squared. Okay, x of t is the solution, or any solution, to our system, but we don't know, suppose we don't know what x of t explicitly is. Okay. So we define this function v, and then let's differentiate that with respect to time, v dot. And this dot notation, it simply means z dot is d dt zt. Okay, it means derivative with respect to time. And v dot is x of t times x dot of t. Okay, for this function. Then that equals x of t times, that's x dot of t is minus x of t. Okay. And then that's minus xt squared. Now, even though we don't know what explicit xt is, still this carries a valuable piece of information. Because of this square, this thing is never negative, okay? And in general, it will be positive unless x of t is 0. And here we have minus sign in front, therefore v dot almost always is negative, okay? So here we have a function defined as such, and we know that we have just figured out, without explicitly solving the system, that its time derivative is negative. Okay? Also, because this function defined in this way, that is, it's the square of something divided by 2, it's never negative, okay? In general, it will be positive unless x of t is 0. So we also know that v is positive. So here we're talking about a function that can never go below 0, okay? And its derivative is always negative. And then that means v must converge to 0 as time goes to 0. Okay? That is V and T is 0. Since this derivative is always negative, it has to go downwards. Okay? It cannot go toward minus infinity because it has to be positive. Therefore, V has to display, that function has to display such a behavior. And then if this guy is going to 0, automatically it means that x of t, thing that we're interested in the first place, must go to 0. Okay? X of t must go to 0. Here's a simple way which we will develop further later on, and also we will add new tools to it. Here's a way that through which we can obtain the behavior of solutions without actually and explicitly solving for the differential equation that describes the system. Okay, and this basic example tells us what this course will be about, more or less. Okay, so roughly speaking, this course will be about the following. Okay, this course is mainly about, we will talk about some other things also, but the following simple diagram. Given a system, what can we say about the behavior, okay, of its solutions, and how can we say about the behavior of the solutions? Okay, so that's a very rough but not inaccurate description of why we study stability theory of dynamic systems. Okay, now the course outline roughly is as follows. Let me talk about the titles that we will cover as we go along, and then we can start with some basic definitions, okay, for today. The course can be, or the outline can be divided roughly into 4 parts. In the beginning, or in the first part, we will talk about, we will define what a dynamical system is, and then we will give some basic examples to dynamic systems. Okay, so that we will have a rough understanding of what we mean by a dynamic system. We will try to visualize that. And then we will, so that definition is for general order systems, and then we will focus on, for a while, second order systems. Okay? So that's another thing that we will deal with in the first part, second order systems. Okay? And why will we study second order systems in particular? Because first of all, they're simple enough, okay? But they're not too simple, simple enough to contain some richness that cannot be displayed by first order systems. And still, they're rich enough to give us some ideas on higher order systems. Okay? And also they have the advantage that, since they're second order, we can draw the trajectories on a plane, for instance, on a piece of paper or on the plane or on the board. And we will have a visual, we will gain a visual understanding by studying some special second order systems. And that's not the only motivation for studying second order systems, that is understanding higher order systems. The other motivation is that there are many interesting systems that are directly second order. Okay, so that for second order systems are interesting on their own right also. And then once we cover some interesting phenomena through second order systems, we'll talk about a little bit theoretical stuff. There is fundamental properties of differential equations. Okay. part, we'll be talking about existence and uniqueness of the solutions for differential equations. We'll talk about things like finite escape time and also reaching the equilibrium point in finite time, things like that. Certain phenomena that cannot be displayed by linear differential equations, but only by nonlinear differential equations. So that's more or less the first part of the course. In the second part, we'll be dealing with tools. Okay, we will cover tools through which we will be able to study the stability of an equilibrium point for a given system. Among those tools, we will cover Lyapunov functions. Okay. And a method that you may be familiar with from E302, the method of linearization, and also Lassalle's invariance principle. Okay. So basically, this is the second part that we will cover. So in the first two parts, part 1 and part 2, we'll be dealing with systems without any input. Okay, so we will study the behavior, and starting from and in the third part, we will also introduce input to the picture. What's an input? We will define soon enough, and we'll consider input both as a good guy, okay, something that we can manipulate in order to make the system behave in a way that we want it to behave, and also we will also look at the input from the other point of view, that is, we will consider it as a bad guy. That is, in that case, we will try to determine whether the input disturbance can hurt us, and if it can, how badly can it hurt us. Okay, we will try to understand, or we will try to develop tools through which we can answer such questions. Okay, and the basic things that we will study will be the following techniques. Backstepping is one. It's quite a standard nonlinear design tool. We'll talk about input state stability. We'll talk about the so-called L stability, which studies the input-output relationship for a given system. And within L stability, we'll talk about an important theorem, small gain theorem, that belongs to nonlinear system theory. And finally, we will spend some time on a very powerful tool for both analysis and design. It's called the tool for passivity. Okay. And that's the third part of the course. And in the last part, first of all these three parts, they will be dealing with continuous time systems, okay? That is, systems where we have dots, okay? A derivative differentiation with respect to time. In the last part, we will briefly talk about certain extensions of what we have seen here to discrete time systems, okay? Which also can have many important applications in discrete time systems. Okay. And if we have time, we will close the course by that deed observer design for a discrete time system. Okay, so that's the rough outline of what we're planning to cover in EE 555. Okay. Now, let's talk about some examples for dynamic systems, but before that we have to be clear about what we mean by a dynamical system. Okay? So let's introduce some definitions first, and then we're going to see how those definitions manifest themselves in some simple examples. a dynamical system or a dynamic system, or sometimes even shorter, just a system is such that it's modeled by a finite number of coupled first order differential equations. Ordinary differential equations. Okay, as follows. So we have, suppose, first equation x1 dot equals, it's a function of possibly time, and then x1, x2, xn, these are the state variables. Then we may also have inputs u1, u2, up. Okay, so time derivative of x1 may depend on all those variables. Likewise, x2 dot is described by a function, possibly of all those variables, x1, x2, xn, u1, u2, up. Okay, and so on. Xn dot equals f of n, t, x1, x2, xn. Now, in this description, these x's, they're called state variables. x1, x2, xn. Okay. They are real numbers at any given time. And then u's, they denote the input variables. Okay. u1, u2, up. Okay, each of them is a real number. And then we have t, always indicating time. Okay, time t. Okay. It may start from anywhere, but where it starts from, we take to be 0. Okay, and it can go as far as necessary, okay, from 0 to infinity. Now, this is the mathematical description of, therefore this is the model of some system, but we just ignore the difference between a model and a system, and we will directly call the model our system. Okay, so that's something that we should keep in mind. That system and model, they're actually different things. Now, for the sake of compactness, certain notations are introduced. So what we do is we stack all those individual variables, x1, x2, up to xn, and make a vector, and we're going to call that vector from now on our state vector. Sometimes the word vector is dropped, and we directly call it the state of the system. Define vectors. Okay, x is x1, x2, xn, u1, u2, up. Okay, and then we can also put these n functions into a vector and define a vector of functions, and that will be our right hand side. Okay, f txu equals f1 of txu, f2 of txu, fn of txu. Okay. So x, therefore, is a vector in Rn, because each of those variables are scalars, and u will be a vector in Rp or in some subset of Rp, and f will be a function, okay, or a mapping that maps this product space to n-dimensional space to Rn, because x dot equals f, x belongs to Rn, therefore x dot also belongs to Rn. Therefore, whatever this does, it must map to Rn. Okay. Then we write or we rewrite this n individual first order scalar differential equations compactly as follows: x dot equals f of txu. Okay. And x dot simply means x1 dot x2 dot up to xn dot. Okay. Dotting a vector means you take time derivative of every single entry. So that's our system, okay? X dot equals, or the compact way to write our system, x dot equals f of txu. In this representation, x is called the state, or sometimes the state vector, and u is the input or the input vector. Sometimes it's also called the forcing term. And then associated to this system, x dot equals f of txu, or associated to this differential equation, sometimes there comes an algebraic equation, non-differential equation, and that equation may be necessary to define the so-called measurement or the output. Okay. A non-differential equation sometimes describes the output. Okay. Or the measurement that you take from the system. And the first measurement is h1 txu, y2 is h2 txu, and these h's are functions of txu in general. And the qth individual measurement is a function of, again, txu. Then you put all these things into this compact form, y equals h of txu. Okay. This is the equation 2. Here y is the vector that you obtain by stacking all these individual measurements, y1, y2 up to yq, and h is a vector function that you obtain by stacking all these individual functions, h1, h2, hq, like you did with f. Okay? And you obtain the so-called output equation. Okay? If this, for instance, describes the engine of some car with many state variables, and from those two state variables, from those many state variables, suppose you make two measurements. One of them is the temperature inside the chamber, and the other is the pressure inside the chamber. And let's take the third one as the rotations per minute. If those are your three measurements, but the actual engine may have many other states, okay, that you do not measure. Those three measurements, they form your output, okay, the temperature, the pressure, and the rotations per minute. And then you stack them and form this second equation, for instance. Okay. Now, this is the most general form for a system description. Sometimes the right-hand side, f does not depend on the input, and then you have x equals f tx. That is, if you don't have any input, then that will be an unforced system. Sometimes it doesn't even depend on time, then you have x equals f of x, and that's called an autonomous system. Okay. So let's write them down. Unforced system equation. Suppose your system doesn't have any inputs. In that case, it would read something like this: x equals f of tx. Autonomous system equation by which we need time invariant and unforced. In that case, we have x equals f of x. So that's the very first example that we have given. The very simple RC circuit, x equals minus x. That fits into time invariant unforced category. Now, having defined what we mean by a system, okay, equation 1 and sometimes equation 1 and equation 2 together, they're called the system. Then associated to any system, a very important property is the so-called equilibrium point. Now, for a given system, an equilibrium point x eq, okay, it's a point in space Rn. Note that the space Rn is a space where the state vector resides of an autonomous is a real root of equation f of x equals 0. Note that f is f that appears in x equals f of x. X is in Rn, therefore x that is in Rn, therefore f is in Rn. Hence, f of x equals 0 in this equation. This 0 must be the 0 vector in space Rn. Okay. So you solve this equation, or you solve n individual equations for x. Okay. And then that, if it has a solution, if it has a real solution, and that each one of those real solutions makes an equilibrium point for the system x equals f of x. That is, if this is an equilibrium point, x eq, then x eq must be the 0 vector. Okay, note that. If you start your system from an equilibrium point, then it remains on that equilibrium point for all future times. Okay, we're talking about the autonomous system, which is that's why we call it an equilibrium point. It implies the solution x of t, starting from this initial condition, equals x eq. And for linear systems, 1 and 2. This is the state equation, and that's the output equation. Okay, 1 and 2. Take the following form. Can be x that equals a of t x plus b of t u, and y equals c of tx plus d of t u. Now x was vectoring Rn, and u was a vectoring Rp, and y was a vectoring Rq. Okay, therefore this must be an n by n matrix with possibly time varying entries. This b of t must be an n by p matrix with possibly time varying entries, and c of t is q by n, and finally d of t is what? Q by p matrix. Okay, so this is the general form for a linear time varying linear system or linear time varying system. If all these matrices A, B, C, and D, they are constants. Okay, the entries are constant. Then what we have here is a linear time invariant system. Now, after this very general or the most general definition, which we will be studying throughout this course, let's apply that to something that we're familiar with and see what happens to what definition. Okay. So here is perhaps the most famous nonlinear system, that is the pendulum. Okay. We have a pivot, and to that pivot we have a rigid rod, which we assume to be massless, of length L, and here we have a mass, okay, mass of N, and this is the direction of the gravity, therefore that's the force that's equal to the pull of gravity, okay, and this is the line, this is the vertical line, and let this be the displacement from the vertical line. This is the angle theta. Okay. Now, for this system, equation of motion is ml theta double dot plus mg sine theta plus KL theta dot equals 0. Okay, so let's call this equation 3. Now this is a description of this system, but it does not, in this form, it does not fit into the form that we introduced, okay, in the previous page. This here is the friction term. Okay. Now let's describe the system according to our notation, that is x that equals f of x, because the model or the system is time invariant, okay, and also it has no forcing term, therefore there is no input. Okay. So note that equation 3 is time invariant and unforced. Okay. And what we're going to do is we're going to put this equation or this description into the standard description, which is x that equals f of x. But before that, let me mention something. Now we said that this equation 3 is time invariant. And what would it be like if it were time varying? Okay. Now here's one way to see the difference between time varying differential equation and time varying differential equation. Suppose that this is in a parallels. Okay. So it describes something, some system that you want to make an experiment with, and suppose that that system is, or your experiment is very, very sensitive. Okay. To gravitational constant. Okay, if it's really, really sensitive to gravitational constant, then you can no longer take the gravitational constant as a constant. Why is that? Because this is determined by the Earth. It's around 9.81. Okay, but it's not only determined by the Earth. If you think about it in through the general picture, it also depends on other bodies in the universe. Okay, it's the nearest thing to the Earth is the Moon, and depending on the position of the Moon, the gravitational pull that this mass will feel will be different, because depending on the position of the Moon, G will be the effective G will be different. Okay, therefore, if your parallels is very, very sensitive, then instead of taking this G as constant, you have to take it time varying. It's varying because the position of the Moon with respect to Earth is changing. Instead of G, you should have here G of T. In that case, if you have G of T here, then this system or that model becomes time varying. But if taking G constant is an accurate enough of model, then as it is, it's a time invariant and unforced system. Okay, now let's put this equation 3 into x that equals f of x 4. Okay. So for that, what we need an x. And what's x? X is the vector that contains our state variables. Okay. x1, x2 up to xn. What's n? N is the order of the system. For this case, we have double dot. That's the highest order term. Therefore, the order of the system is 2. That means we require 2 state variables in order to be able to write x that equals f of x. What are those 2 state variables? Well, there are many choices, but usually what we do is we stick to the physically meaningful choices. And the physical meaningful choice for this case is the angle, okay, theta, and the angular velocity, which is theta dot. Okay, so suppose let us take x1 as theta and x2 as theta dot, and by that choice we can easily obtain the right hand side f. So let's do that, and once we have x equals f of x, we can also figure out whether the system has any equilibrium points. Now choose states as x1 as theta, and this notation, column followed by equal sign, it means we're defining x1 here. Okay, x1 is defined to be theta, or choosing x1 as theta and choosing x2 as angular velocity, theta dot. So this is the angle and this is angular velocity. Okay. Now once we have the states, and this is the description of the system that we're given, we can easily obtain the right hand side, x that equals f of x. Because x1 dot is theta dot and theta dot is x2. Okay. Therefore, that's the first entry of our f. How about x2 dot? Okay, x2 dot is theta double dot, and theta double dot is here. So this is x2 dot. What you do is you throw everything else to the other side. You divide both sides with m times l, and what we have is x2 dot in terms of x1 and x2. Okay, and if you do that, x2 dot equals minus g over l sine x1 minus k over n x2. Those are our individual state equations. And now we're going to put those individual state equations into a single vector state equation. Okay, so that means our state vector x is x1 and x2, and f of x is such that this is f1 and this is f2. x2 and minus g over l sine x1 minus k over n x2. So that's our state, and that's our right hand side. And x that equals f of x with that choice is also a description of the same system. Okay. Now the next question is, since we have now x that equals f of x, to figure out the equilibrium points. Equilibrium point or points, if there are any. Okay. For that, we apply the definition. We equate right hand side to 0. F of x equals 0. This is a vector, therefore this 0 is the 0 vector. Okay, 0, 0 in R2. So this reads, okay, let's write f in its open form. x2 minus g over l sine x1 minus k over n x2. Okay. Equate this to 0 vector to figure out equilibrium points. So this directly gives us that x2 must be 0. So at any equilibrium point or equilibrium point candidate, second state must be 0, which makes sense because second state is angular velocity. If something stays, therefore the velocity must be 0. Okay. So x2 equals 0. And this thing must also be 0. Remember that x2 is 0, therefore we can forget about this term. And what we have is minus g over l sine x1 equals 0. So that means sine x1 equals 0. And that means x1 can be 0 or pi or 3 pi, 2 pi and so on. Okay. So that means x1 equals 0 plus minus pi plus minus 2 pi and so on. Any integer multiple of pi for x1 and x2 equals 0 would therefore give us an equilibrium point. Okay. Hence, any one of these can be an equilibrium point. 0, 0, plus minus pi, 0, plus minus 2 pi, 0, and so on. So what we have is we have multiple equilibrium points. Okay. Even though here we have infinitely many equilibrium points, physically, if you look at the physical picture, we see that there are 2 actual equilibrium points from the physical point of view. And we all know what those 2 equilibrium points are. Okay. Physically, we have 2 equilibrium points. Okay. One of them is this one, 0, 0. 0, 0, and the other is pi 0. Okay. Now 0, 0 is this equilibrium point that is the pendulum is pointing down and stays motionless. Okay. theta equals 0 and theta then equals 0. So this is that, and how about the other one? The other one, okay, the other one is this. Now theta is now pi, and theta that is 0, that means it stays in vertical position, and this is pi, theta equals pi, and theta dot equals 0. Okay. And for instance, 0 minus pi is, okay, if you go minus pi, that means you go pi degrees from the other way, from the other direction. Again, you reach the same physical point. Or theta equals 0, theta equals 5 pi, again, corresponds to the same physical position. Okay, likewise, theta equals 6 pi, and theta equals 0 corresponds to the same physical position. Therefore, physically speaking, we have only two equilibrium points. This is that. Okay. Later on, we will see, once we define what's stable and what's not, but everybody more or less has some vague idea on what's stable and what's not. And we know from experience, from the real world, that this is a stable equilibrium point, and this one is an unstable equilibrium point. Okay? There is a slight disturbance to that will make the pendulum move away from the equilibrium point, but slight disturbance to that equilibrium point will not make the pendulum move arbitrarily far from the equilibrium point. Therefore, this is called stable, and that's unstable. Of course, the precise definitions will be given later on. Okay. In our next lecture, we'll be talking about some further examples where we define state and obtain the state equation x equals f of x.